Hi, I'm Lexi Stone.
I'm Madeline Edenton.
And today we're going to talk about the Königsberg Bridge Problem. But before we take a look at the Königsberg Bridge Problem, we're going to take a look at some simpler shapes. Can you draw a line between vertices only once without picking up your pencil? Pause the video here and try these shapes out on your own. Alright, now that you've done that, what is this called? A path that visits each vertex and travels on each edge only once is called an Eulerian path. Which ones worked? Keep in mind, there are many different solutions. This is just an example of one possible solution. So for shape 1, we were able to find an Eulerian path. For shape 2, there does not exist an Eulerian path. Shape 3, also no Eulerian path. Shape 4, multiple different options, but this is one possible solution. For instance, you could have the exact same path in reverse also as an Eulerian path. Number 5. There was an Eulerian path, multiple, here's one.
Alright, so here are some things that we can notice. How many points and vertices did each shape have? How many lines and edges did each shape have? How many edges did each vertex touch? We call this the degree of the vertex. So here's a degree 2 vertex and a degree 3 vertex. So how do we know which one will work? Do we just have to guess, or can we find any patterns? So let's start counting number of vertices and figuring out how many are even and how many are odd. So for shape 1, it did work. There are 4 vertices, 4 of which are even because they're degree 2, and there are no odd degree vertices. Shape 2, we can do a similar thing, but all 4 of our vertices are now odd. Shape 3, 2 even and 4 odd. Shape 4, 4 even and 2 odd. And shape 5, all 5 are even degree vertices. So what does this mean? What is the answer? Well, you can tell that an Eulerian path exists if the number of vertices with odd degree is either 2 or 0. If there are 2 odd degree vertices, they have to be the starting and ending vertices. So for this shape, the starting vertex is odd and the ending vertex is odd, but all of the other vertices are even. So why is this the case? The degrees must be even so that each line that leads into a vertex has another line that leads out. The starting vertex can have an odd degree because the initial lead out did not require a lead in to be paired with it. The ending point similarly can have an odd degree because the final lead in does not require a lead back out to be paired with it. So degree 2 works, degree 3 doesn't work, unless it's the starting or ending vertex.
So this is famously called the Königsberg Bridge Problem. Can you walk through the town and visit each region but only cross each bridge once? The history of the Königsberg Bridge Problem. So the Pregel River divided the town of Königsberg, Prussia into 4 distinct regions, 2 riverbanks, a peninsula, and an island. According to lore, citizens made a game of trying to go to each region without crossing the same bridge twice. None of the citizens could figure out a solution, but they also couldn't prove that it wasn't possible. A man named Karl Eller wrote to the famous mathematician Leonard Euler for a solution, but Euler didn't think it was related to mathematics and thought it was too trivial for his attention. But the more he thought about it, he noticed that the problem could be related to a topic still underdeveloped, geometry of position. This is now known as graph theory. So on August 26, 1735, he published the solution. But let's try to find his solution on our own.
So how can we simplify this diagram? Well, we can make all the bridges look like this and reduce the city down to this little link shape. So first we can label the regions with letters and label the bridges with numbers, just to make notation easier for ourselves. And we can notice that A is connected to C by bridges 2 and 3, B is connected to D by bridge 7, and this goes on for all the bridges in all the regions. So now we can let each region be a vertex, let each bridge be an edge, keeping in mind how many bridges connect each region. So we can relabel all of our bridges and regions, and we retain the original positioning. So A is connected to B by 2 bridges, C by 2 bridges, and D by 1 bridge, etc. So how many degrees does each vertex have? Well, if we look at our drawing and count our vertice degrees, we see that vertex A has 5 degrees, B has 3, C has 3, and D has 3. So what can we notice? All of the vertices are odd degree. What does this mean for the residents of Königsberg? Well, in short, they were wasting their time. We can use our knowledge of how the degree for each vertex matters, and we can learn that since we don't have 0 or 2 odd degree vertices, there does not exist an Eulerian path for this diagram, and so we can't visit each region and only cross each bridge once. So now we've solved the bridge problem just like Euler did. No such path exists.
So what are the implications of Königsberg Bridge Problem? The Königsberg Bridge Problem and Eulerian Paths led to the development of the foundations for both graph theory and topology. Graph theory is the study of graphs and the relationship between objects. Euler's paper published on the Königsberg Bridge Problem is actually considered to be the first paper in graph theory history.
The Königsberg Bridge Problem is also considered one of the first 2 theorems in the field of topology. Euler's study and paper on the problem is regarded as the very first practical application of topology, which is the study of how spaces are affected by continuous deformations. As an extra resource, we have attached a worksheet working with Eulerian paths, so you can look at some different shapes, some new shapes, and also try and figure out if there's a way you can fix the Königsberg bridges so that there is a solution. We just want to say a thank you to Dr. Millichap, Furman University, and of course, Leonard Euler.